continue on electrism cosmology.
Thank you. Yes, I know my writing is bad, so there are a set of lecture notes coming out. Actually, these are notes of talks I gave in Brazil quite a long while ago, but they still hold, except they don't talk about inflation, but you're getting inflation from other people in this course. So now, just to remind you, the metric we use in cosmology, ds squared is minus dt squared. There's a universal time in cosmology. The scale factor, and what I should have emphasized, if you look at this metric, this spatial part, there is no time in there. The only place the time occurs is in the scale factor, and that's why it is the scale factor, is because in this metric, that is the only place where time occurs. This is all just spatial stuff, and I discussed it yesterday. The fluid motion is delta A, 0 is 1, 0, 0, and what that means is in space-time, we have our surfaces T is constant. These are preferred surfaces associated with the preferred velocity, which is orthogonal, and so we have our preferred motion of matter in the universe, as I discussed with you yesterday. Now, we were talking about matter and the thermal history. And my problem here is there's a huge amount of physics to do with the thermal history. What we discovered was for matter, the density is a constant over A cubed, conservation of matter. For radiation, the density is a constant over A to the fourth, which implies that the temperature scales is 1 over A of T. And we did both of those last time. Now, this, as I said last time, says that we have a hot Big Bang, and basically in the universe, if we plot the scale factor as a function of time, the scale factor over today's value, and we have the temperature, and we're going to take the logarithm of the temperature, we have a logarithmic scale with the temperature today being 3 degrees Kelvin, today being the background radiation temperature, and as you go back, the temperature in principle diverges. As the temperature diverges, the energy density diverges. So we have another graph here, which is the energy density, the logarithm, over the scale factor A over A naught. And that is a slope minus 1, corresponding to 1 over A. Now, this is the temperature going as 1 over A to the fourth of the radiation. The matter goes... Well, all right, now, what I need to do, and it's laid out in these notes, but what we need to do is to notice the main physics things that happen as we go back. And there's a series of physics things that happen as we go back in the universe from today to earlier and earlier times. And the first thing that happens is the photon energy becomes greater than the binding energy of anything. So you take any structure you like. Take an atom. As you go back, we exceed the binding energy of the atom at about 4,000 degrees. Atoms become ions. The ions and the electrons are then freely, and so the universe becomes a plasma. So atoms go to ions plus electrons. In other words, the universe becomes a plasma at about a temperature of 4,000 degrees. Okay, the nuclei get broken up into protons and neutrons at about 10 to the 8th degrees. The protons and neutrons get broken up into quarks, and so on. Anything that you think of has got a binding energy. And when the temperature of the universe gets bigger than that binding energy, it's going to get split into its parts. And so as we go back, the universe at recent times has got all these molecules that we see around us here. Go back, I should have said, molecules go to atoms as you exceed the binding energy of the molecules. The atoms get broken up into ions and electrons. The nuclei the nuclei get broken up into protons and neutrons. The protons and neutrons into quarks, and if quarks are made of any subparticles, those will get broken up as well, because you exceed the binding energy. So as you go back, the universe gets made up of simpler and simpler things, more and more elementary particles. That's point number one. Point number two is at these temperatures, we have thermal equilibrium of the plasma. Now, that's because the ionization time, the time for interaction, is much less than the time for expansion. And you have to put in the numbers to check that out. You have to look at the rate at which the universe is expanding. And even though at very early times it's expanding very fast, the interactions you're concerned with at those times are even faster. And so what you get is thermal equilibrium of the plasma with a changing temperature. Okay? Because the collisions are so fast that they bring you into thermal equilibrium. Now, that has a very, very nice feature, because what it means is you don't have to know the previous history of the universe. Supposing, for the moment, that in fact, I have assumed up there that the scale factor just increases with time from zero. We'll talk about this shortly when we get to the field equations. But supposing there was a bounce from a very big temperature, we drop to some temperature and then go back up again. Sorry, the scale factor drops to a small factor and then back up. What would happen to the temperature? The temperature would drop from low to a maximum and then go back down again. The temperature wouldn't be monotonic anymore. It would reach a minimum and go back up. It doesn't matter what you throw in beforehand, provided your temperature gets high enough, everything you throw in gets broken down. And so it doesn't matter what you throw in beforehand. You get an equilibrium mixture. One of the great features of equilibrium, it's highly unique. You just need to know the temperature and what the mixture of particles are, and you know what the equilibrium result is. And so,
Yeah, may I interrupt?
Yes.
But for the benefit of the student, not to make a comment, as yesterday I gave a lecture on back of the envelope calculations, and one of the things I did is to calculate this 4,000 degrees.
Okay.
Except, because it was back of the envelope, I got 5,000 degrees.
Okay. Yeah.
But it's the same calculation
Yeah.
that Professor Ellis is talking about. And also, to make sure the students are not confused, I unfortunately used a different notation from Professor Ellis. So what Professor Ellis calls the scale factor is A of T, or A of temperature, is what I call capital R yesterday.
Capital?
Roughly called the radius
L.
of the universe.
Okay.
Roughly refer
All right.
to physicists, we're talking about the same
Sure.
thing.
Okay. Thank you. Well, when I was young, it was called R of T for the radius factor.
Right. That's what I used.
It became S of T for the scale factor. One of the things you have to get used to in physics is changing notation.
So obviously I'm older than you.
Okay, now, so it doesn't matter what you threw in, you get thermal equilibrium. Now, then, what becomes now really important is you have a kind of a problem. Because your radiation scales as 1 over A. If you take a simple model of matter, monatomic gas, the temperature of the matter scales as 1 over A squared for a simple monatomic gas. We can have a big argument about whether that's a good approximation, but the key point here is this isn't the same as that. So now we have a kind of a theoretical problem. Your matter wants to go at one temperature, the radiation wants to go at a different temperature, but they're in equilibrium with each other. So what happens? Which one wins? And the answer is the radiation wins, because if you calculate the thermal capacity of the radiation, it is hugely greater than the thermal capacity of the matter. Now that's a really astonishing result, because we had to do incredibly delicate measurements to measure the microwave background radiation. We had to use our best detectors, supercooled, and we find this 3 degrees incredibly low. If you just use standard gas laws and calculate, you find the amount of heat in the radiation is about 10 to the 8th times the amount of heat in the matter. Now, why is that? For the very simple reason, this radiation fills the whole of space where the matter is concentrated in tiny clumps. And so it's because the radiation is everywhere that the radiation wins out. And the temperature of the matter, when they're in equilibrium, is equal to the temperature of the radiation, and they go as 1 over A. So that is then a really important point to notice, that the matter and radiation, because they're in equilibrium, the temperatures have to be same, and so which one wins? Well, the answer is the radiation wins. Okay, now, the third point is pair production. And the point here is that there is a rest mass energy for every particle. And as the temperature goes up, what you will be getting is you will be getting photons colliding with other photons. And when the energy is high enough, the rest mass energy will be exceeded. And so, for instance, you will get electron-positron pair production taking place when you exceed that temperature, which is of the order of 10 to the 10. A little bit higher, you will get proton-antiproton. Higher, you will get, think of any particle pairs you like. As the temperature goes up, you will exceed the rest mass energy or whatever you think of, and you will get pair productions of those particles. Now, what this means over here is that in this temperature as a function of time, there's actually a little step in there, because as you come down in temperature, the inverse process takes place. As you come down in temperature, what happens is the electrons and the protons collide and give you photons. So the matter feeds into the radiation, and there is in fact a little step here which shifts you from one curve here to a slightly different curve. Okay? Now, I'm trying to summarize a huge amount of physics in a very short time. One thing I should have added about thermal equilibrium up here is even neutrinos are in equilibrium at a high enough temperature, T greater than about, let's say, 10 to the 11th K. I'm just giving you rough temperature scales. That's a truly extraordinary statement if you think how difficult it is to measure neutrinos. They go through the Earth without being noticed, all the rest of it. At high enough temperatures, the neutrinos themselves come into equilibrium as well. Now, the consequence is that as you come down, the photons are giving you a photon background here. The neutrinos, there is in fact a neutrino background as well as a photon background, and the neutrino background is at about 1 degree K, a little bit lower because of this step here. So if you could detect neutrinos, and this is now would be one of the great experiments of cosmology, verifying the standard or model, if you could do it, as well as being embedded in the sea of photons, we're embedded in the sea of neutrinos, background neutrinos coming from the very, very early stage of the universe. The temperature is incredibly low, so detecting them is, I'm not an expert, I would take it as impossible, but if you could measure it, there are these neutrinos floating around through the whole universe as well as the photons. Okay, now, so what we get is we get equilibrium abundances. Equilibrium abundances of particles at each temperature in the very, very early universe. And the fourth and final kind of thing that I need to mention, and you will hear much more about this from other people than from me, but I just want to mention it, forces will be unified at high enough temperatures. The electric and the electromagnetic force and the weak force will be unified at the electro-weak force early enough. That will be presumably unified with the strong force early enough, and at even earlier times the gravitational force. Now, I'm not going to discuss this here. I'm just saying that this is one of the things that will happen. Because in the early universe, every temperature, as long as there is an initial singularity, which I will discuss shortly, every temperature you can think of is exceeded. And so every branch of physics, through atomic elementary particle physics to quantum gravity, will be called into play unless we avoid the singularity. So that's a really important question. Okay, so now, as we go forward in time, we've been thinking of going backward time. As we go forward in time, everything will happen in reverse. The neutrinos will decouple. Shortly thereafter, the electron-positron pairs will feed into photons. And then at about 10 to the 8th degrees K, we get nucleosynthesis. And this is one of the great achievements of nuclear physics combined with cosmology in the mid-1960s, 1970s, in which, going forward in time, basically the simple elements combine to give you simple molecules. And this has been discussed in enormous detail the basic kind of reaction is a proton plus a neutron giving you deuterium plus a photon, and then deuterium plus deuterium giving you helium-3 plus a neutron, and then helium-3 plus a deuteron giving you helium-4 plus a neutron. And so what's happening there is proton capture, and you're building up the light elements. And there's a huge amount written on this, and in fact, for instance, Weinberg's book, The First 3 Minutes, is a really, really nice introduction, and we don't have the time or space to go into the details of this, but the basic point that happens is light elements are synthesized, and by light elements what I mean is deuterium, helium-3, helium-4, lithium. And then there is a bottleneck in the production of higher elements, and that's as far as the early universe goes. So, this leaves us with a kind of a massive problem that we have to solve. If we look around the room, now in fact what happens here, and of course we've got hydrogen, and the hydrogen is 75%, and all of this lot is 25%. Well, in fact, it's the helium, which is 25% basically. And it cuts off at lithium. So the question is, where does the carbon, nitrogen, oxygen, phosphorus in this room come from? And you surely know this, but I just want to get the full picture. The heavy elements are formed in stars, first generation stars, and then spread in space by supernova explosions, and then lead to second generation stars. So this was a discovery of the 1960s. Second generation stars can have planets. First generation stars can't have planets worth speaking of because there's no heavy elements to make the planets. And so this is one of the major discoveries. As the universe expands, you get nuclear synthesis taking place, light elements up to lithium, and that's as far as it goes. So you do not have the materials to make life by the time you come through at the end of nucleosynthesis. Nucleosynthesis comes to a stop because the temperature drops below the threshold for nuclear reactions. And after that, you've just got these elements left. And so what happens then, the crucially important feature is that the first generation stars form, and they cook the nuclear elements for a very long time, and they can create elements up to and including iron. They then blow apart, spread these through space, and this then coalesces to form second generation stars with planets.
Just before we get to the heavy elements, what happens to the antiparticle?
Oh.
In the picture, after pair production.
Okay, there's a whole thing which goes on here. The belief is that particles and antiparticles are very, very closely matched, and then there is a slightly out of equilibrium process which gives you a slight preponderance of particles to antiparticles. This has been the discussion through the decades. There was one group of people who suggest the universe is exactly particle-antiparticle symmetric, and what has happened is particles have coalesced out somewhere and antiparticles out there, so some of those galaxies up there are antiparticles, and you better not travel there because you'll be in deep trouble when you arrive there. It's more commonly thought now that instead, that isn't quite what happens, that there's a slight asymmetry in weak interactions which produces the asymmetry of particles to antiparticles, but it depends on an unknown particle called the X, which could, and it's one of these speculative things that we know the conditions it could happen, but we don't actually have a specific mechanism. And Professor Z will know a huge amount more about this than I do. Okay, now, the hugely important further thing that takes place is the following. As we go through, coming down, these things all go the other way. We build up, and the crucially important one is when ions and electrons form atoms. Because when you've got ions and electrons, the universe is opaque, and it's opaque because of Thomson scattering. because free electrons scatter very, very strongly with photons. And all of a sudden you get atoms. And this is at this temperature, this ionization temperature of about 4,000 degrees Kelvin. So all of a sudden, what were free electrons and proton nuclei become bound atoms. And all of a sudden, the universe becomes transparent. And it's a very, very dramatic transition that takes place. So this is at what is called decoupling. Why decoupling? Because at this time, the matter and radiation, which were in equilibrium, are now decoupled. And so the universe becomes transparent. And a model for this is what happens in the sun. As you cross from the interior of the sun to the exterior, the photon mean free path changes from at most a few centimeters to thousands and thousands of light years. In fact, here it changes, the photon's mean free path changes from less than a centimeter to 1,000 million light years. The universe is unbelievably transparent today. That's one of the things what you should remember about it. We are seeing back to these incredible early times with basically no interference, but we are cut off by the surface of last scattering. So the surface of last scattering or surface of decoupling is the limit to which we can see. As we go back into the past, as the photons, it's transparent until we hit that time. It is this surface which emits photons which cool today to give us the 2.75 degree K microwave background radiation. So the microwave background radiation we can think of as being emitted by the surface of last scattering. These photons have then traveled freely towards us for thousands of millions of years, and we receive them today with these very sensitive detectors. But the point about it is that the universe was opaque before and becomes transparent at this time. Okay, now, what else is there? I'm not going to say much more about all of this at this time. I think that's as much as I'm going to say about all of these interactions. They are hugely complex. They're a great deal of fun to work out in detail. The nucleosynthesis details were worked out in about 1965 to 1970, were completed, as it were, and nothing much has changed since then. And so these are the processes to remember. The binding energies, everything gets broken up going back. They form going forward. Thermal equilibrium at these temperatures, and the temperatures follow the radiation. Pair production going up, pair annihilation going down. The forces will be unified at early enough times, but that's rather speculative, and I'm not going to go into that. And in these processes of building up, one of the most important is the nucleosynthesis, when we build up the light elements, but we can't build up the heavy elements because the universe is expanding too fast and the temperature is dropping too fast. And so the heavy elements must be created later on in stars, which are then spread through space by supernova explosions and allow second-generation stars to have use for planets. And then decoupling, there's the matter and radiation decouple, and the universe, which was completely opaque, suddenly becomes completely transparent. And that's a really important part of cosmology. And the radiation which was emitted at that time, we can think of the surface as emitting these photons. That's what we measure today as the background radiation, the 2.75 K radiation. Okay, how do we know all of this is true? Firstly, because we measure the cosmic background radiation at 3 degrees K, and second, we measure the element abundances. And I'm not going to go into the details of that, just to say that these agree with each other. It's most people's views. There are some problems. We don't know the interaction rates of the nuclear reactions as closely as we would like. One of the problems also is that the elements which are formed in the early universe then get messed around by stars. So what was the primeval abundance is not necessarily the abundance you measure in the light you get from stars at later times. So there's quite a lot of complication in this, but nevertheless the basic agreement is that these agree, and they agree provided the density of baryons is about 0.02 in the dimensionless units which we will be using. And this is really important, that this agreement comes only if the amount of baryons is approximately this amount, 0.02. I'll be talking about this quantity omega shortly, but just, yeah, but we will need to remember that figure for later on. Okay, I want to get on to the relativity side of all of this. So, that's as much as I want to say about all of this lot, and I want to get on to the evolution of the universe itself. So, section 5, and you will be getting a copy of these notes, is the origin of the universe. Okay, so all of this, what we need to know is how does the scale factor behave? That's one of the things we need to know. Okay, now, to calculate this, you can calculate this in many ways. I'm just going to give you a brief note on the best way to do this. The best way to do this is to take the Ricci identity for the scale factor, for the... we've got our preferred velocity. And what you can do is take the Ricci identity. For general relativity people, every single vector in a space-time must satisfy this identity. Now what you do with that is you contract it with the 4 velocity again. So you contract it with a C, and then you set A is equal to B. If you do that, you end up with the single most important equation in cosmology, which is the Raychaudhuri equation. 3a double dot t over a of t plus kappa upon 2 into mu plus 3p, rho plus 3p minus lambda is equal to 0. And you get that from this equation by contracting with the u and then setting a as to b, which is contracting over a and b. And this equation will result, there are some more details in these notes which you will be getting out. Now this equation is what I'm going to call the Raychaudhuri equation, because an Indian gentleman named Raychaudhuri found that this applied in much more general circumstances, as I will say a word about probably in the last lecture. Now, why is this important? Because of the following. What you can do, you can plot A as a function of time, so A is a function of time. What does this equation tell you? It tells you A double dot. Now, what is A double dot? When you have a curve A of t, A double dot is the curvature. It is the rate of change of the slope. The slope is the Hubble parameter, and the rate of change of the slope is given by A double dot. And you immediately see from that A double dot is less than naught, is greater than naught. Now, hang on, I must get the signs correct here. A double dot is less than naught. A double dot is less than naught if mu plus 3p is positive and if lambda is less than or equal to naught. What that means is this curve is bending down going forward, but at the moment, at the present day t0, we know that the universe is expanding, so at the moment it's sloping upwards. If you have mu plus 3p positive, then that gives you a negative contribution to A double dot. Now lambda can give you either. If lambda is negative or 0, then that also bends down, and what that means is the following. We get the basic and most important singularity theorem. And the singularity theorem will be as follows. If lambda is 0, let's take that for simplicity, and mu plus 3p positive, then A of t goes to 0 a time t0 less than 1 over h0 ago, where the energy density will become infinite and the temperature will become infinite. And this is the basic singularity theorem. It's telling you the Einstein field equations. I should have emphasized that you use the Einstein field equations which is where the lambda comes from and the rho plus 3p comes from. What it says is the following. The slope of the universe, a straight line will give you 0 a time 1 over h naught ago. If rho plus 3p is positive and lambda is 0, then this curve must bend down. So as you go backwards, you must run into the axis before this time 1 over h naught. So the age of the universe is less than 1 over the Hubble constant. The Hubble constant being a dot over a evaluated today. So that's the slope of this line. This height here is the age of the universe, is the present scale factor of the universe. And this curve runs into 0 a finite time ago, where that time is less than the inverse Hubble parameter. Now, this is one of the most central features of cosmology, the Singularity Theorem. Because it's saying there's a beginning to the universe, according to classical general relativity. And I just want to say a word or two about this. Nowadays, in cosmology, people talk about the beginning of the universe in a kind of a casual kind of way. They sort of say, oh yeah, there was a beginning to the universe. They have forgotten how shocking a concept it is. There is a start, not merely to physics, to matter, but to space and space-time itself. And so always people sort of ask the question, what happened before the beginning? Well, the answer is there wasn't a before the beginning. Our language doesn't actually even allow us to talk about this properly. We inevitably look at this graph and say, okay, what was happening over here before the beginning? There wasn't any time here. You see, what I need to do is to scrub off the whole thing, including the axes. Nothing existed before here. And even to say nothing existed is still too strong, because exist doesn't mean anything at a time when there wasn't any time or any space or anything. And we have got so used nowadays to the idea, if people talk about the singularity or a start to the universe, we have forgotten what a shocking concept it is. Out of nothing. But you see, nothing is not a vacuum. A vacuum is a lot of stuff, which you will hear from prophecy. Not out of nothing, really nothing. Not time, not space, no physics, nothing. The thing comes into existence. And that is a really shocking concept if you think about it. Which is why throughout the history of cosmology, people have tried to find ways of avoiding a beginning to the universe. The temperature diverges, the pressure diverges, the scale factor goes to 0, so the metric tensor goes wrong. You lose the spatial dimensions at that time. You end up with this universe at that limit where there's no space. Space doesn't exist. Actually, time doesn't exist either. So, this is a really important thing. Is this true? Can we get around it? Okay, this is if lambda is naught. So, okay, what about with the positive cosmological constant? And it's been known since the 1930s that a positive cosmological constant can avoid the singularity. You'll find it in that article by Robertson I mentioned to you yesterday. So why don't we say we'll put in a positive cosmological constant? Well, you see, the problem is the following. Throw in a positive cosmological constant, and you'll get a solution which can bounce, or it can be asymptotic to the Einstein static. You can get two singularity-free solutions like that. So why isn't that a good model of the present-day universe? Well, the problem is that lambda had to win in this equation way back there at some time in the past. Now, we're up here. We know the universe has expanded by at least a factor of 1,000, okay, because of the microwave background radiation. At that time, the cosmological constant was the same, but the energy density was 10 cubed, 1,000 cubed, bigger. It was 10 to the 9th times bigger than today, because it's gone as 1 over the scale factor cubed, and the scale factor was 1,000 bigger. So down here, at the time of decoupling, the density was 1,000 times, was a 10 to the, is that 6 or 9? 6 times bigger than today. But the cosmological constant was the same. If the cosmological constant is to avoid the Big Bang, it has to have the same value here as here. There's no way we could ignore that cosmological constant, because it would have dominated the universe way back down then. It would be hugely dominating the universe today. It would be much, much bigger than the measured value of the cosmological constant. So, if you imagine a cosmological constant which will solve the Big Bang problem, then today we would still be accelerating. We would be accelerating so fast we wouldn't have to do tiny measurements to measure the acceleration. It would be absolutely obvious. And so the cosmological constant can solve it in principle, yes, but in practice, no. Or to put it another way, the cosmological constant can solve it if you come to a modified form of cosmological constant which gives you a bounce or an asymptotic Einstein static and then decays away. In other words, if you don't have a constant but a scalar field which decays away, and there are such models which I will refer to later, but a straightforward cosmological constant cannot solve the initial singularity. Okay, can we find matter for which ρ plus 3p is negative? Well, when I was a graduate student, the answer was no, but nowadays the answer is supposed to be yes. And the answer is supposed to be a scalar field will solve that inequality. Now, why is that? It's because a scalar field, it's written down in these notes here, and I'm not going to worry about the units, but roughly speaking, a scalar field is equivalent to a fluid for which the energy density is phi dot squared plus 2 times plus the potential energy, and the pressure is equal to phi dot squared minus v of phi. A scalar field in a Robertson-Walker model is equivalent to a fluid, and this is a scalar field phi of t with a potential v of phi, and it can be shown quite easily that it's equivalent to a fluid for which rho is phi dot squared plus v of phi, and the pressure phi dot squared minus v of phi. If you just put those into rho plus 3p, you immediately see that rho plus 3p, well, that is 4 phi dot squared minus 2v by adding 3 of those and 1 of those. And that is less than naught if phi dot is much less than v. In other words, a scalar field, if it is slow rolling, if it is moving very slowly, can violate the energy condition. Now, firstly, that's what enables inflationary universes to happen, as will be discussed later on. But it also is quite clear here that this offers at least the possibility of avoiding the initial singularity in the universe. I'm going to return to this shortly. There are various people who are saying that in inflation there is no way of avoiding the initial singularity, but actually they're wrong. And I will show you they're wrong shortly when we get on to the rest of the field equations. I want to just spend a little bit more time with the Raychaudhuri equation because it is such an important and such a fundamental equation in cosmology. What that Raychaudhuri equation tells you is the following. Let's just go back to Einstein and ask about a static solution. Let's ask, I want to have a static solution of the Einstein field equation, which means A of t is a constant, so A dot is 0 is A double dot. Put that into this equation here, and you see lambda is kappa upon 2 into rho plus 3p. If you're going to have a static universe, that's what you're going to need. Now, a little bit of history. When Einstein first set up the field equations, he didn't have the cosmological constant. And he effectively discovered this theorem in an indirect way because he had a 0, and because in those days nobody believed, well, in fact, he was dealing only with matter. So he had the equation lambda is kappa upon 2 rho, in effect, because he wasn't looking at the pressure. Initially, he didn't have the cosmological constant, so he couldn't get a static solution. So what he did was he looked at the field equations and he worked out, actually, I can include the cosmological constant. It's a possibility it's there. And if it's there, it gives me a static solution, even if there's no pressure. And if there is pressure, it'll still give you a static solution. So Einstein introduced the cosmological constant in order to get the static solution. I'm saying where that comes from is from the Raychaudhuri equation. Why did he want a static solution? As I said yesterday, because at that time everybody knew that the universe was static. That was just commonly accepted as being the wisdom of the time. So one immediate conclusion from this equation is that if you've got a static solution, then lambda must be positive if you've got ordinary matter. Lambda must be positive if you have ordinary matter. And that's what Einstein discovered in 1917. it has an even more useful thing for us here. Let us suppose we have got an Einstein static model. So here's A of t, and it's exactly constant. We've got this Einstein static model. Now, what physicists want to know is that stable or is that unstable? Always one of the questions you ask is the stability. So let's assume we can slightly perturb the universe till it's just above where it was. Okay? Now, we need to go to that equation there. A double dot over A is equal to minus kappa upon 2 into rho. I'm just going to use the matter. The pressure complicates it. Let's just use the matter to see what's happening. Supposing we have a static solution and we now perturb it, so it's now just a little bit above, what will have happened? Well, what will have happened will have been the density will have decreased because we have expanded a bit. But the lambda is the same. So the density is decreased, the lambda is the same. So if you perturb it just a little bit, these exactly balanced in the static solution. This is now dropped, and this is now winning, so this is now positive. So now we are bending upwards. So we're going to bend a little bit up more. So we end up at new point. At that new point, the density is dropped even more. Lambda is still the same. The second derivative is even more positive, so we bend up even more. And we have an exponential instability of the Einstein static universe. This is what was discovered by Eddington in 1930. And it is this fact which, in my view, persuaded people that the universe was expanding, was the discovery that the Einstein static universe was unstable. If you push it a little bit down, what will happen then, if you push it a bit down, is that the density will increase. And lambda will be the same. This will then be negative, so it will bend downwards, and it will follow a catastrophic path into a singularity. So from the Ray-Choudhury equation, we deduce, firstly, you need a cosmological constant if you have ordinary matter to get a static solution. And secondly, you deduce that the Einstein static universe is unstable. So most physicists then say that means the Einstein static universe is not physical because it's unstable. Now, let's just step back a minute and think about that. Can we perturb the universe? Well, the answer is no. The universe is everything there is. And if the universe is there, you can't perturb it unless you go outside poking your fingers inside somehow to the universe. So in fact, this idea of perturbing the universe is not a viable idea. The way we would rephrase this nowadays is in terms of fine-tuning. You have to get the balance between the scale factor and the lambda infinitely accurately right in order to balance it. And even quantum fluctuations, should they occur, would now threaten this. So the point about it nowadays would be to say, when we say it's unstable, what we would say, I think we would rephrase that nowadays to say, look, you need infinite fine-tuning to achieve the exact balance between the cosmological constant, which is trying to push it apart, and the energy density, which is trying to hold it together. You need infinitely accurate balance and infinite fine-tuning, and that is what most people would regard as unphysical nowadays. So that would be a different way of stating this.
Do you know what Einstein's response was to Eddington's discovery?
Well, I think it's basically that's when he accepted the expanding universe. Because it's really remarkable, this, I've written a little historical paper on this. Friedman paper 22, second one 24, Lemaitre 27, they were all ignored, even though until a crucial meeting of the Royal Astronomical Society in 1931, where Eddington presented this. Okay, so now, for ordinary matter, we have the problem of the origin of the universe. What happens at this Big Bang? Well, one way of stating this nowadays would be we exceed the Planck energy. And then the classical approximation that I'm making breaks down, and so quantum gravity takes over, and we must use some other theory of gravity to see what happens. And so currently the way we would express this would be to say what this is really saying is, given standard physics and the standard Robertson-Walker model, what is inevitable in the early past is quantum gravity, which may or may not solve the initial singularity of the universe. The standard wave function of the universe scenario does not solve it, but the loop quantum gravity scenario does solve it, but we don't know which of those is correct. Okay. So what we would say here is that, in fact, nowadays we would reinterpret this to say, what this is saying is the classical regime, as we go back, will end and we'll enter a quantum gravity regime, and we must work out what happens in quantum gravity, and that will decide if there is a singularity or not. That would be the way we would phrase this nowadays. Okay, now just a caution. When we do this, we are assuming the Einstein field equations are correct way back to the start of the universe. Now there's two horrendous extrapolations taking place. Firstly is physical scale. Let me ask you, on what scale have we tested Einstein equations? And the answer is, we have tested them on the scale of the solar system. They are incredibly well tested at solar system scale. They are not tested even on the scale of our galaxy or the clusters of galaxies. So in spatial terms, they have not been tested on the kinds of scales that are involved. Secondly, the tests in the solar system are basically static tests. The dynamics that is involved here have never been tested in any astronomical or physical observation. In fact, Engelbert Schucking once talked about this and said it's a little bit like in Maxwell's theory, if you had known only the Coulomb force had been tested, and you said this predicts electromagnetic waves. There is a huge extrapolation from the static solutions in the solar system where we test general relativity to the dynamic solutions here. And the third point is there's an incredible extrapolation back in time to physical conditions which are totally different from the present day. Now, I believe the Einstein equations are true back at that time because they are so unbelievably unique. They're incredibly unique. But that is a huge extrapolation. So one way around all of this is to say it's all based on the Einstein equations, and who knows if the Einstein equations are true, A, on those scales, and B, at those times. Well, physics, we have to take what we know and extrapolate what we know, and so we have to take the Einstein equations because they're the best we've got. But I'm just saying, if you want to say what other ways are there out of the Singularity Theorem, one is to say, well, let's violate the energy condition, which we can do with scalar fields. And one is to say, I don't believe the Einstein field equations at those times or on those scales. Yes?
Isn't the Hulson-Taylor, the pulsar timing experiment, Hulson-Taylor, isn't that enough to
it's very
dynamics?
Well, it's solar system scale.
Yeah, but it does produce an energy loss.
It's very weak dynamics. I mean, I agree.
It's dynamic.
It's dynamical. It's a very, very weak field limit. This is not a weak field limit. Okay, now, let's get on with the rest of this and talk now about the evolution of the universe. Okay, now we've got this field equation here, and there's a remarkable feature that happens. What I must remind you of, we have the energy equation, rho dot plus 3 A dot over A into rho plus P is naught. And a remarkable thing happens. Take this equation, multiply that by A dot squared times A and integrate. Multiply this by A dot. And you can integrate it, given this equation, and you can integrate it to get the following equation. 3s dot squared minus kappa mu s squared minus lambda s squared is a constant. And that is a first integral of the other equations. And this is the famous Friedmann equation, the equation Friedmann discovered way back in 1922 for the case k is plus 1. Now, what you can do is spend a bit of time looking at that, and what you find is this constant is in fact the spatial curvature. Now, I don't have time to go into the details of that, which will be in these notes which I'm giving out to you, but I want to give you the canonical form of the Friedmann equation. 3s dot squared over s squared minus kappa mu minus lambda is equal to minus 3k over s squared if you spend a bit of time doing Riemannian geometry, trying to examine this constant, you find this is that, where k is nothing other than this k here. And so what you get is really important different signs in this equation. This is the spatial curvature constant, which we've got up there, and that is the Friedmann equation, which we have to solve, which is the first integral of Ray-Chowdhury. What that means is it's a first integral provided that you're expanding, and we now will leave the static universe behind. So what it means is what you have to solve in cosmology is these two equations. Oops, sorry. It's what you have to solve in cosmology is these two equations for the standard model. Now, this is indeterminate until you give an equation of state P is P of rho. Sorry, I keep on into... in my notes, I've got a mu or a rho. You'll have to get used to mu and rho being interchangeable for the energy density. Okay, this is what we have to solve. So what we have to do, specify an equation of state, solve for the energy density, put the energy density into here, and then solve that equation. And so basically, cosmology dynamically comes down to solving that equation. Now, the parameters is the Hubble constant, S dot over S naught. So the Hubble parameter, that's one of the parameters we get. Second important parameter is the deceleration parameter, minus 1 over h naught squared, S double dot over S 0. These factors are put in to make it dimensionless, and that is telling you the curvature of this curve. That is positive if it's bending down and negative if it's bending up. So that is a dimensionless form of the curvature, and the h naught is the slope. So h is the slope and q naught is the curvature of this curve. And then what we do here is we express the matter in terms of these parameters omega. Omega is kappa rho over 3h naught squared. And you can get that for the baryons. You can get it for the total matter. So for baryons, you will be the baryon density. For the total matter, it will be the total density. You can get a cosmological constant term, which is lambda over 3h naught squared. And the dimensionless versions of the energy density parameter is this for each component, for your photons, your neutrinos, your baryons, your cold dark matter, and so on. And the total energy density, omega naught, is the sum of those for all of these terms here. Okay. Now, what you can do is evaluate this equation today. Put on a 0 here. Now, today, the pressure is negligible. That's basically the deceleration parameter. That's basically your omega naught. So if you evaluate that today, what you get is Q naught is a half omega of all the matter minus omega lambda. And that is the one equation relating these parameters. The deceleration of the universe is a half the omega of all the matter present minus the omega for the cosmological constant. The second one is that the curvature today, which is by definition k over a naught squared, is equal to h naught squared into omega m plus omega lambda minus 1. That's the present curvature today. And so if you can measure the amount of matter in the cosmological constant, this gives you the deceleration parameter. Or if you have the deceleration parameter, this will tell you the difference between the two. And then the spatial curvature comes out of that particular sum. Okay, if lambda is 0, if there's no cosmological constant, you get Q naught is a half omega m, just that the deceleration of the universe is directly given by the amount of matter, and you get that the curvature, k over a naught squared, is equal to h naught squared into omega m minus 1. And you see that omega m is 1 is the critical value, because that is a flat space section. That is a flat space section if there's no cosmological constant. If it is greater than 1, we have k as plus 1, which I talked about yesterday, closed space sections. And if it is less than 1, we have k as minus 1, which is the hyperbolic case. So immediately you see, if we can get hold of this parameter omega m, and we know lambda is vanishing, we can find out the spatial curvature. It's a bit more complicated if the cosmological constant is non-zero, but this is what will tell you. Are the space sections flat, negatively curved, positively curved, what I talked about yesterday? It will immediately come out from this equation here. And the universe accelerating or decelerating relates these two. If it vanishes, you get these simplified relations. Throughout the 1960s, 70s, 80s, everybody assumed lambda was naught. So Alan Sandage published a famous paper called Cosmology, the Search for Two Numbers. And that was Q naught and omega m he was talking about. Right. Now, what we need to do is look at the nature of the solutions. And of course they are... Let's just briefly look at lambda is naught and the solutions for ordinary matter. Lambda ordinary matter are very, very simple. You recollapse if k is plus 1. You are on the border. This is the scale factor as a function of time if k is naught, and you expand forever if k is minus 1. Now that immediately follows from these equations here. And what I just want to point out here is the Friedmann equation. A turning point of the Friedmann equation happens when S dot is naught. When is S dot is naught? It's when, I must make sure I get the signs correct in this one. It's when kappa mu plus lambda is equal to 3k over s squared. That's when a turning point happens. And so if there's no cosmological constant, you need kappa mu is 3k over s squared. And so that immediately tells you you can only get this if k is positive. The only times that solutions turn around, maxima or minima, is if they are positively spatially curved. Now, this is something which some cosmologists have forgotten nowadays. Any interesting behavior, if you have vanishing lambda, can only happen. In fact, and with the normal lambda, for most people assume lambda is positive. So if you have a positive lambda, if you have positive matter, which all ordinary matter is, the only interesting cases in terms of turning around. If you want a minimum, if you want to avoid the singularity, not only if you want to avoid the singularity, must you avoid this condition, you must also have positive spatial curvature in order to get interesting behavior. So the turnaround happens for positive curvature, and that happens for the critical density, for critical density greater than 1, here critical density equals 1, here critical density less than 1. That's for vanishing cosmological constant. Now, for lambda positive, all sorts of other behaviors are possible because you can get the Einstein static universe. And I should say that this applies to Einstein static. Einstein static must have k as plus 1 for exactly the reason I've said. And that was the reason Einstein liked the Einstein static universe. He wanted closed space sections. Now, why did Einstein want closed space sections? Because he spent a lot of time worrying about the boundary conditions for physics at infinity. And he said to himself, if the universe space sections close up, there isn't an infinity, so there are no problems of boundary conditions at infinity. You've heard echoes of this in the Hartle-Hawking no boundary conditions for the universe story. Einstein was there in 1917. When he found his cosmological model, actually he wasn't trying to solve cosmology, he was trying to solve Mach's principle and boundary conditions for local physics. And that's where he got this model from, really. And so the point about it is, for k is plus 1, for the Einstein static model, must have k is plus 1. You can get models which are asymptotic to it, which collapse. You can get models asymptotic to it, which expand. You can get models which are non-singular like that. You can get Big Bang models like that. You can get Big Bang models which recollapse. All of these behaviors are possible when the cosmological constant is positive. All of the interesting ones I've just pointed out occur only if k is plus 1. So this must have k is plus 1. This must have k is plus 1. This must have k is plus 1. Right. Now, we can get some exact solutions, which I'm not going to write down, except I'm just going to say there are three important simplest solutions, and it's important to know the simplest solutions in cosmology. And they all have names. And the first one is the Einstein de Sitter universe, which is, ask yourself, what is the simplest solution I can get of these equations? Well, the simplest solution is if I put the pressure to zero, the cosmological constant to zero, and the curvature to zero. That's my simplest solution. Well, it then becomes pretty easy to solve because that term is gone and that term is gone. You've just got those two. And this equation is solved for p is naught. We get the density is a constant over s cubed. So you put that in there, missing those two, and you easily find the scale factor is proportional to t to the 2/3. And most astrophysicists use that model as a background when they're doing astrophysics because it's a pretty good model of the universe since the time of decoupling of matter and radiation. You want to have a background for formation of galaxies, structure, and so on. That's the model people use because it's the simplest one you can get. Okay, that's the Einstein de Sitter universe. And incidentally, the age of this universe is 2/3 1 over h naught, which easily follows. So if you remember here, your limit on the age was 1 over h naught. Well, the Einstein de Sitter model comes in as 2/3 of that value. 2/3 of that value. Okay, now, the next one is the Milne universe. And the Milne universe comes in with p is naught, and the energy density is naught, and lambda is naught, and k is -1. And that's a bit strange because this is now an empty universe, and the scale factor is proportional to t. And in fact, this is empty. In fact, it's flat space-time. So why is flat space-time interesting? The answer is, as a cosmology by itself, it's not interesting, but it is an asymptotic state for many universes. It's not a good model by itself, but it's a very good model of the asymptotics of many universes. And the third one, which is similar, is the de Sitter universe. And for the de Sitter universe, it's easiest perhaps to have p is naught, rho is naught, and lambda is not naught. And then there are many forms that we can look at the form with k is naught, and we get exponential h of t, an exponential expansion for the de Sitter universe. This is the k is zero form of the de Sitter universe. And that again is important because it is the asymptotic state of many universes. In fact, universes with lambda positive that expand forever are all asymptotic to that one. And universes with k is -1 and lambda is naught are all asymptotic to that one. So these are the asymptotic states in the future. The Milne for ones with vanishing cosmological constant, and the de Sitter for ones with positive cosmological constant. Yes. Yes. The space sections are negatively curved. The space-time is flat. In fact, if you're familiar with hyperbolic geometry, what the Milne universe is in flat space-time, it's the sections. The space sections are the sections at constant time from the origin, actually. This is a picture which people may not be used to, but in fact, what the Milne universe is, it's this section of constant time surface is embedded in flat space-time. Okay, now, the other one that's important is in the early universe. What would be a good model for the hot Big Bang era? Well, the answer is P is mu over 3, K is naught, we can ignore the curvature, and lambda is naught. And this is the Einstein de Sitter universe for radiation, and the scale factor goes as t to the 1/2. And that immediately follows again from here. Put in radiation, ignore lambda, ignore k, and you get the scale factor proportional to t to the 1/2. And this, what you then do, is put that back in the Friedmann equation, and this gives you a unique relation of the temperature and the time. If you put that back now, so in this case, what we've got is 3s dot squared over s squared is kappa mu, which is radiation, which is therefore kappa times the Stefan constant times t to the fourth. And so it's telling you the temperature in relation to the scale factor. And this is where the nucleosynthesis time scales come from. It's really important in nucleosynthesis how fast you go through the period of creation of the light elements. If you go through too fast, you don't get any nucleosynthesis, and if you go through too slow, you don't get any nucleosynthesis. And you have to go through at the right speed to get the 75% of hydrogen, 25% helium, which we see today. Now, the De Sitter universe became famous in the 1950s as the steady-state universe of Bondi, Gold, and Hoyle. What they said is they didn't like the Big Bang for exactly the reasons I was saying. They said, let's see if we can avoid the singular state. And so they said, let's think of a universe which is expanding but unchanging in time. Now, what does that require? It requires that the energy density is a constant, and it requires that the Hubble parameter is a constant. If you try to solve the Einstein field equations, you can only solve it if there is vanishing matter. But they said, well, as I've already indicated, we don't know the field equations are true on this scale, so let's modify the field equations. We add in a term which is a creation term. We modify the energy conservation equations. And so they modified the energy conservation so that as the universe expanded, new particles were created all the time. Hydrogen atoms were coming into existence. I think all protons were coming into existence. Now, the rate was negligible. It was 1 proton per cubic megaparsec per century or something like that, that you couldn't measure by any ordinary measurements. But overall, it was enough to give you a steady-state universe. So they got the solution with a modified Einstein field equations. And a lot of time was spent in the 1960s trying to find out if this model was true or not. It was a very good model scientifically because it could be contradicted. It was contradicted by radio sources. Before the microwave background, it was discovered that radio sources could not be static. There couldn't be a steady density of radio sources. And that killed off the steady-state universe. It got even more killed off when the microwave background was found, because it's difficult to explain a microwave background in a steady-state universe. But I'm just saying that now you can also get the steady-state universe if you it's just the universe with just a cosmological constant. And it's important to realize a cosmological constant is exactly the same as a fluid with rho plus p is 0. I mentioned this yesterday. I'm going to mention it again. Whenever you have a cosmological constant, you can say it's a cosmological constant, or you can say it's a fluid in which rho plus p is 0. Because, as I pointed out yesterday, in that case, this is 0, and therefore rho is a constant, so the density is a constant. So a fluid with rho plus p 0 is a constant, and that is exactly the same physically, macroscopically considered, as a cosmological constant. Okay, now, there's lots of fun things we can do with the dynamics of these models, and I mustn't do too much of it, but I'd like to do some of it. Jeff, how long do you want to continue? All right, maybe what I'll finish off this time with is a nice phase plane. Whenever you've got a system of equations like this, as mathematicians, it's good to go, let's see if we can find phase planes, because they tell you a huge amount in a simple space. And this phase plane comes from a paper by Stabel and Refstal, and most of you won't have seen it because it's monthly notices of the Royal Astronomical Society in 1966, volume 132, page 379. And what they do is they plot a very nice phase plane in which this parameter is what they call sigma naught, which is omega naught over 2. One of the changes of notation which has happened, the mathematical cosmologists in the old days called the density parameter sigma, and it differed by a factor 2 from what is now omega. And along the bottom is the deceleration parameter. And what you have here is minus 1, 0, 1, 2. And up here, in terms of sigma naught, we have a half, 1, 2. And in this phase plane, you draw there's a critical point, which is the point a half and a half. And that's the Einstein de Sitter universe. The point a half is the Einstein de Sitter universe. And there's a curve, a straight line curve through there, and that is the curve vanishing cosmological constant. And on this side, the cosmological constant is negative, and on this side, the cosmological constant is positive. And there's another curve you can draw through here like that, and that is the curve k is 0. And on this side, k is plus 1, and on this side, k is minus 1. Okay? Now, this solution here is Einstein de Sitter. A key point here. This solution here is Milne, and this solution here is de Sitter. These three simple models that I told you were important. And what you get is a beautiful set of evolution curves here. Now, the Einstein de Sitter universe is a fixed point. If you're Einstein de Sitter exactly, you stay there forever. You can't get up. Oh, sorry, I should have said this is for p is naught, but for arbitrary values of the cosmological constant. So this is for dust. Okay, one solution is this model which goes up here, and that is an Einstein static universe. Einstein de Sitter perturbation, which reaches a maximum and then recollapses. So that's a universe which goes to a maximum and recollapses. This is a model which just expands forever. So these are the vanishing cosmological constant solutions on this line. The Einstein de Sitter, the one which just reaches infinity, the ones which recollapse on this side, and the ones which expand forever on this side. Okay. This is a solution, and okay, what the solution curves look like is they look like this. That's a solution, these are solutions. Now there's a critical curve here that comes down, and these are the ones which collapse, which are non-singular in the past, and these ones here are non-singular in the past. And this is the one which comes down as an asymptotic to the these are the ones which collapse like that, and this is the one which was asymptotic to the Einstein static and then expands forever. So this is non-singular because it was Einstein static in the past and then expands forever. All the ones here in this shaded green area are the ones which recollapse. So these have got infinite age. You get solutions which come like that, and then ones which go like that and like that. And that's a phase plane for dust universe models with a non-vanishing cosmological constant. Now, where are we? Which one are we? And the current values, which I will come to later, but the current value which people believe in is omega about 0.7 and omega matter about 0.3, with the total omega m close to 1, but maybe a little bit positive. And what that would suggest is being where is it? I'll have to work out where that is. I haven't plotted that on this diagram. Sigma naught. It's one of the ones which is asymptotic to over here, so it'll be a little bit positive. It'll be something like about there, on a model which is going to expand forever. One of the interesting things in this model is, so what you can see now is that the de Sitter universe is the attractor in the future for all models with positive lambda, which expand forever. The de Sitter is the attractor for all such models. The Milne universe is the attractor for models with the special case lambda is naught, but it's unstable. If lambda is slightly positive or negative, it goes off in those directions there. The Einstein de Sitter model is the source for all of the models. In this, notice that this is the pressure-free case. This won't be accurate at very, very early times, and there is an extension of this diagram. Ellis and Rindler have got a very nice extension of this to matter plus radiation, and that is in monthly notices of the Royal Astronomical Society about 1987. I'm not sure exactly of the date, but they give an extension of this, an accurate one, which includes matter and radiation, which means they have to have a third direction. So it's much more complicated. They have a matter direction and then a radiation direction, and their model, they have a version of this in which they take into account non-interacting matter and radiation. And that's a very nice model, which a phase plane model which they have, of the exact non-interacting matter and radiation in the early universe. I think we've had a pretty long session, so I think we'll stop at this point. I'm going to show you another phase plane tomorrow, and then go on to start talking about observations.